the ISC. Today it's my pleasure to introduce Raul Abramo, who is visiting us during this month using this UNDARK project. So he's mostly working with the cosmology group and in particular with Carlos. So who is Raul? Raul actually has already come a few times, at least last year he was around. He also gave a seminar on a completely different topic. Raul is a cosmologist working on the interface between observational cosmology and theoretical cosmology. In fact, he participates actively in different surveys, the most prominent of one of which I would like to emphasize is JPAS, in which also Carlos is actively involved. He graduated in Brown University in '97, and then he did a few postdocs, first in Florida University and then in Munich University, until he landed in University of Sao Paulo, where he is now a senior research staff. So his broad expertise in cosmology, most recently, he's getting machine learning, by the way. He gave a very nice seminar last year about this. But now he's part of a group in Brazil which is trying to get into the Einstein telescope to start working also on gravitational waves in cosmological context. That is what he is going to talk about now. So Raul, thank you very much for coming, for giving this talk. The floor is yours.
Oh, thank you. Can you guys hear me okay there and on Zoom? All right. So thanks a lot for the invitation, and thanks for Carlos and especially Jorge Martin Kamalich for this for making possible for me to visit the ISC. So I'm going to talk about something completely different from some of the stuff that I've done before, but I think it's really one of the ways of the future in cosmology, and I think everybody should be paying attention if they're interested in learning more about the universe, which is in the impact of the observation of gravitational waves from mergers of compact objects. And this is becoming quickly a new window into the universe, and there are many ways of exploring that, of connecting with your physics, with your astronomy. It will be another way to look at the universe, right? I have this, and I also have, okay, so I have many ways of pointing to things, but so this is work that we put out a couple months ago, and it's basically accepted to JCAP. It's done together with my PhD student, João Ferri, who is now in Japan in the EPMU, my other PhD student, Ian Tashiro, also Isabella Matos, who is a postdoc, but now she's in Portsmouth, and Miguel Quartin and Ricardo Sturani, who are over here. So let me just start by reminding you that there are many ways of observing the universe, not only through optical and near infrared and through galaxies and quasars and so on, but increasingly we are seeing the universe through the light, not the light, through new messengers also. And gravitational waves is one of those messengers. It's we rely on these very sophisticated interferometers like LIGO, Virgo, and Cagra, which are now a network of observers of let's say telescopes. They are, in all respects, telescopes, and they've been observing a wide variety of events, some of which are very spectacular, like like neutron star mergers that everybody heard about, the kilonova in 2017, and also black hole mergers, which do not create, as far as we know, any electromagnetic counterparts. So they are entirely seen only in gravitational waves, and they are much, much more frequent than neutron star mergers. So we have only seen one kilonova so far, and we have seen order of 100, 150. Now, actually, the data that's coming out from LIGO, Virgo, and Cagra will be of the order of 200 of those events. And what's interesting here is that for the kilonovas, which are, of course, spectacular because we see them both in gravitational waves and in the optical and near infrared, and they give us amazing insights on many things, including an impact on the distance, on H0, right? We'll talk a little bit more about that later. But we see many, many more black hole mergers, binary black hole mergers. And this is something that I want to exploit here, is that even without an electromagnetic counterpart, there are ways in which we can explore this information to know more about the universe, specifically about cosmography. So how do we do that is critical here, because gravitational waves, as opposed to optical, infrared, electromagnetic, they have zero, they care nothing about the galaxy. Or even if we were surrounded by 1 million suns nearby, they would be completely oblivious to this. Gravitational waves, they just cross everything. They don't care. So we see the entire sky with gravitational waves. So it's critical that we have the machinery that can describe the full sky with gravitational waves. And that machinery is not necessarily putting the universe into a Cartesian box, because that's not how we see the universe. We see the universe through the past light cone. So we see the universe as shells in redshift or distance, if you want. And we have the idea that if the universe is homogeneous, that each shell, along the shell, if you look in the angular direction in a given shell, things should be isotropic, right? So we have to go away from the picture where I'm going to just use my mouse here. Otherwise, I have to, I'll have two injuries out of instead of just one. So instead of using a box, a Cartesian way of representing things, which is okay if you're just looking at a small piece of the universe. But if you're looking at the entire past light cone, this is obviously not true. But the main ideas stay, so are still the same. So one of the critical tools that we have is a two-point correlation function, which in Fourier space is just the power spectrum. And that power spectrum has some noise, which is related to the number of objects that you are observing. That's called shot noise. And typically for galaxies, this is a concern, but not a huge concern. For binary black holes, this is a huge concern. And this is something that I'll come back to. And one of the ways of overcoming that concern is looking at the cross correlations of those gravitational wave signals from those black hole mergers. Okay, so another concern is that we cannot simply look at the universe in these shells, and we cannot just project everything into very, very thick, very broad shells, because then we lose information. There is evolution, things are not the same between redshift 0.1 and 0.2, but they're not even the same between redshift 0.2 and 0.21. We have to be able to distinguish those shells, and we have to have the machinery to decompose the universe into many, many of these different shells, right? So everybody is aware here of the cosmic microwave background, which is basically one very thin shell at a redshift of 1,000. And I'll show you that with gravitational waves and galaxies together, we have to look at the universe into many hundreds of thin shells around us in our past light cone. So basically, the idea is that we have something like this. Each sheet here is a time equals constant hypersurface, which of course we have no access to. This is inaccessible. This is a theoretical construct. What we see is only this light cone here, right? And what we see is at a given redshift, we see something here on that shell here, which is I'm representing as a circle, but actually it's a shell, right? And if you look at farther away from us at a different redshift or at a larger distance, we see another one of those shells there. And of course, we cannot do infinitely thin shells, because infinitely thin shells don't have any objects in them. We have to use something that carries the information that we need without smearing out, without erasing that information, right? So there's a bunch of, there are many techniques for dealing with this. This is an idea that goes back many years, back to Peebles and others, right? But there is a difficulty here that I should make you aware before I jump into the actual application that we did, which is the following fact. Well, what are we doing here is that we are counting objects. Those objects may be galaxies or black hole mergers inside those thin shells. Like here, I made these shells a bit thicker now so that you can visualize that, right? So we integrate those objects inside a shell there, and then we basically compute the density of those objects, or the overdensity, right? And then we decompose that into the proper basis for those spherical shells, which are spherical harmonics, right? So this can be done in terms of the field level, or if you can do in terms of particles, it doesn't matter too much, right? And then you have to correlate those things. Well, how do you correlate? That correlation is called the angular power spectrum. It is exactly the same thing that you do for the CMB. And in the case of counts of objects, that carries also some shot noise here. I'm counting here. These are, I'm decomposing here the number counts. So the shot noise appears in this way. If I was doing the density contrast, you have 1 over n, but that's how it is, right? So it's just like the CMB, just that the CMB doesn't have the same expression because it's a field. It's not a count of points, right? And then you have to look at each one of those slices and each one of those angular scales called L, right? We believe that Universidad is isotropic, so M, the angular momentum projection M just goes away when you do the average here, but the angular scale L remains just like the CMB, right? But then look at how many degrees of freedom you end up having, because L is anything that goes from 1, the dipole, 2, the quadrupole, all the way to whatever L maximum you can resolve with your maps, right? That L max can be very large. For Planck, L max is what, 2,500, something like this, depending on what you want to do. For some other CMB instruments, it might be 5,000 even. But look at this. These are the number of shells that we have. And these shells, like I told you, we don't want to just project everything and lose all the redshift or distance information. We need many shells. So this now becomes a very complicated problem, because if, let's say you have 100 shells, then the number of cross correlations is like 100 square. And that times the number of angular scales that you have. So your summary statistics, which is the angular power spectrum or the power strength, is not so summary anymore. It is a very, very large set of numbers. And that becomes an issue. And you have to solve that issue before you attempt to do anything, right? Okay, so this is a very crude way of representing this. So this is basically, these are all the 2-point combinations that you can do with, I think in this case, we did like something like 50 shells. And this would be kind of the correlation matrix of these angular power spectrum. So it's a huge, huge, large dimensional thing. And it has a complicated structure. Of course, you can imagine that because of the correlations in the universe, nearby shells are tightly correlated. But if you have thin shells, those correlations extend beyond the shell that you are to nearby and more and more and more, right? So this is a complicated object, and you have to know how to deal with that. In principle, you have the number of dimensions of your observable would be, your covariance matrix would be around this. And this can be like 10 to the 6, 10 to the 7, 10 to the 8. There's no way that you can compute a sample covariance matrix like this. No way ever we're going to be able to do this. So there are some ways around this. So there are semi-analytical ways. And in a paper that we published in 2022, we found a way of going about this. I don't want to show you this more than just to show you that there is a way of writing the covariance and its inverse in the Gaussian approximation. So in this work, and in fact, pretty much anybody that works in this field, they have to do something like this. You assume that your degrees of freedom are Gaussian. In that case, the 4-point function, which is the covariance of the 2-point function, is a 4-point function. That 4-point function, because of the Wick theorem, reduces to something which is simple, and then you can invert that and go on. So that's the lesson here. There are ways of doing this analytically or semi-analytically, but this is for another time. The technicalities we can discuss at some other point, okay? Now, let me get down to business here, which is the interesting thing. Gravitational waves. So if you took general relativity as an undergraduate student, you may have seen something which is, you may have seen derive an analytical expression for this here, which is the power emitted by a pair of compact objects of points which are orbiting each other, right? So this is an undergraduate level exercise to compute what is the strain of the gravitational waves emitted by a pair of compact objects. Of course, as that pair comes closer and closer, this problem becomes, you have to use perturbation theory, some other tools or numerical tools to compute that exactly. But, you know, this is a very, very simple problem. These are zero-dimensional objects. I mean, there's spin to them, but basically they are very simple objects. You can derive these expressions here basically analytically. In fact, people have devised ways of doing perturbation theory now to fourth and fifth order, so it's incredibly precise. The systematic errors in the modeling of these strains emitted by the pairs of black holes are basically negligible, okay? So what that strain here in the two polarizations that are emitted here tells you is that it depends on the mass of the objects, it depends on the angle that they have with respect to your line of sight, but for the most part, what goes in here is the distance. What you observe on Earth with respect to the actual power that's emitted at the source goes like 1 over the distance. And it turns out that if you know that mass, you measure the frequency, you can know that distance. So by measuring those two strains, you can derive that distance with some error, which is actually very large, okay? But you can derive the distance directly. So bottom line, which is something that some of you may know, some of you may not know, gravitational waves do not give you the redshift. You have no access to the redshift. What you measure is the distance, luminosity distance. Actually, it's not even luminosity distance because in different gravity theories, this can be slightly different. So you have kind of modifications to gravity. This becomes something slightly different. But let's say we are working in general relativity. That is the distance that you have there. So as opposed to galaxies where we have no access to distance, we have access to redshift, okay? So that's basically it. These are extremely simple systems. This is not like a Cepheid star or a supernova or a giant red star that we need to calibrate somehow. We know this. Physics tells us directly we don't need any calibration for this. There's no systematics here. Okay, there's error, and these distances are known with sometimes 5%, 10% errors, but that's precision, that's accuracy, not precision. They are precise, even if they may not be accurate. You measure the waveforms, you derive the rest. There's no, of course, this is a simplified formula, but when you go to second, third, fourth post-Newtonian order, and you do the numerical calculation, there's no systematics there. There's basically no error in there. The error comes from the detection. Your detectors are imperfect. No, there's degeneracy. There's a perfect degeneracy between the chirp mass and the redshift. So if you knew the mass, you would know the redshift, but there's a perfect degeneracy you don't know. So that's one way in which people try to sometimes deconvolve the mass, let's say the mass function of those binary black hole mergers and get at the redshift. But that's a very dangerous game that depends on the prior because nobody really knows what is the mass function for these binary black holes, right? Okay. All right. Mass is degenerate with redshift. Redshift. This chirp mass here is the redshifted chirp mass. So we don't know precisely what it is. So whenever you see LIGO is giving you the mass of that pair, that is based on knowing of getting a m times 1 plus z estimate together with the distance. Then in the standard cosmological model, they invert the distance to get the redshift, and then they tell you the mass. That's how they do. All those plots, they are based on this. Okay? So we have no access to the mass of redshift, only to the distance. Okay?
Let's say that with let's see this frequency, this dynamic. Do you have any vision on that frequency? Or
yeah, the frequency goes like mass to the something like 8/3 or 5/3, right? Minus that, right? So the larger masses have lower frequencies, and that frequency changes as you approach the merger, right? So that's how there's a sensitivity to the frequency and to the rate of change of the frequency. And that frequency, as long as it stays within within the bandwidth of your detector, then you see that object, right? And each detector has a different bandwidth depending on the levels of noise. I'll come back to this later. Yeah. You measure this, and you measure the dependence of the frequency. Using that, you measure the chirp mass, and you infer the distance. With the two polarizations, of course. And that's why it's important to have a network. With a single one, it's much more difficult to get the two polarizations because it's just one combination of them that you see, right? And that's how they combine, they work much better. Okay, so how can you use those observations? Well, the most clear case that we can have is from the 2017 kilonova, because we see both redshift, because it was observed, it was detected. Everybody immediately, all the telescopes in the world that could do it, they immediately started to search for electromagnetic counterparts because LIGO warned everybody, hey, this is very likely a neutron star merger, right? And we actually detected that. So basically, there was a superposition of the LIGO area with the area that was also determined by the gamma ray observations from Fermi. And then people searched in that place and they found this tiny little speck of light here, which turned out to be exactly what people expected for neutron star merger. So we find the progenitor. It was difficult, but in this case it was possible. And then from the gravitational waves, you measure the distance, which is about 40 plus or minus 10 megaparsecs. So you see a 25% error. That's what you get from the present generation of gravitational wave detectors. And then you can imagine that this is more or less the game that you play here. You have different values of H0, right? You measure for one of them, you know the redshift, which is about 0.01, sorry, and you measure the distance, and then you have, okay, here is more or less what you get from that single observation. That's a very crude exercise, but that's more or less it. And that's what they found here, this curve, which is over there with that single object. What you see here is the Planck prediction for H0, and this is the Shields supernova prediction for H0, and that's basically what you're seeing here is the so-called H0 tension, which is now at the level of like 5 sigma. That we know that the Planck value, the CMB derived value for the H0 is much smaller than the value that you infer on the basis of Cepheid stars and supernovas in the local universe. And then nobody knows really how to solve this. It's there. I mean, people have been working on this for more than 10 years now and doesn't seem to be going anywhere. In fact, with the James Webb Telescope, it's getting worse. But anyway, I'm getting ahead of myself here. The point is that these types of observations of gravitational waves, they can, even with a single object, they can already start shedding some light. So you see that it's consistent with the two of them, even though we cannot break the tension. Now, you could also use so-called dark sirens. Dark sirens are sirens which you don't see with electromagnetic signals. So black hole mergers. So you never see them, never see light from them, right? So there are ways of inferring the value of H0 by inferring the redshift of those sources. And that goes more or less in the direction of the question that Jorge asked, because we can kind of break the degeneracy between mass and redshift if we make some assumptions. There are many ways of doing this. I'm not going to talk a lot about this. They are very weak constraints, and they depend on priors. They are very, very, very much depending on priors for the distribution. So there are two main methods. So it's called spectral sirens, which is what Jorge suggested here. And also there's something called line of sight method, which is kind of a similar idea. You use the galaxies as a prior to where the black holes are. So I'm not going to discuss this too much. This is another method of using dark sirens. So everybody clear here? Dark sirens are basically black hole mergers, and there's little or no hope to ever seeing any light from them unless they happen inside an AGN disk or something crazy like this, which is a possibility, but you know. Okay. Now, what is the future looking like? Well, right now, we started with LIGO, which is over here, and LIGO got updates, run 2, run 3, which ended just a couple years ago, and run 4, which is basically on the way, happening right now, and it's every time that they do this, they increase the, they enhance the instruments, they make it more sensitive. They reach also deeper into the universe. The frequency range isn't changing too much, but the sensitivity is. They are making their lasers, their interferometers more sensitive. What's going to happen in the future is that now that we know there are tens, hundreds, possibly thousands, tens of thousands of sources out there which are not that difficult to observe, people are thinking, well, we should enlarge our frequency range, make our detectors more sensitive to get more events. So this is the idea behind going further to the next generation of observatories, and the two main ones are called the Einstein Telescope, which is an European initiative, and the Cosmic Explorer, which is an American one. So the Europeans are more ahead of the game in this. There is a collaboration called, there's a well-established collaboration. So we are part of the Brazilian chapter of that collaboration, but you know, it's like there's a budget, but there's no money yet. However, it seems that the instrument is very well underway to be funded. And the first, so here is an idea of what the LIGO looks like. Here's what an idea about the first, let's say, design concept for the Einstein telescope was. Instead of having a 4-kilometer arms, they would have a triangle with 10 kilometers. The important part here is that ET, the Einstein telescope, would be underground. And the reason for that is that gravity waves, which are not gravitational, gravity waves are seismic disturbances, which are the main source of problems for all of these gravitational detectors on Earth. You cannot go to lower frequencies because you are affected by anything from the truck driving 10 kilometers away to literally waves in the sea 20 or 30 kilometers. They do introduce some background noise, and you have to put things on underground because these seismic waves, they travel on the surface. So by putting things underground, you are able to shield your detection from them. So the present design of Einstein telescope is moving away from this triangle to two interferometers, two L-like interferometers, one which is going to be in the border between Holland and Germany, and another one which is going to be in Sardinia. I'm all for the one in Sardinia. Islands are good. And the Cosmic Explorer is a proposal in the US, but it's a bit more in the future. It's going to be like this, you know, really, really long 40-kilometer one or two of these detectors, and it's not clear when or if it's going to be funded. But that's it. So what do you expect to see with the Einstein telescope? Order of 10,000 to 100,000 events. Redshifts up to 10, maybe 20. We don't know because we don't know how many objects are out there. We only know what LIGO tells us, which is much more than we expected. So 10 to the 4 events per year with Einstein telescope, right? So anyway, so let me move ahead because otherwise I would maybe talk about my own research here. So with that in mind, let's think about this. We observe galaxies in redshift. So we point our telescope, we scan a region of the sky, we see these galaxies here. We have no idea about the distances where they are. We can make assumptions, we can impose a model, and from that model give the distances, but what we actually know is the redshifts, right? On the other hand, we have these black hole mergers, which are 99.9% of all gravitational waves events. I mean, so far, we have seen one neutron star merger, and in order to see the electromagnetic counterpart, it has to be really close, because if it's very far away, then we will never see any counterpart. It's basically impossible. So we have these two pictures of the sky. We have galaxy surveys now that map almost the entire sky, and we have gravitational waves which are mapping the entire sky with different sensitivities, but the entire sky. And we know the distances with extreme precision, even though with low accuracy. So what if we can combine these two together? And that's the basic idea here. How can we combine them and then get some information about that, how we can cross-match the distances in the redshift? Of course, we cannot do this object by object. And the reason for this is that the gravitational wave detections of these black hole mergers are very uncertain. Just so that you have an idea, the typical size, even with the Einstein telescope, of the region where you think your signal is coming from one particular black hole merger is a few square degrees in angle and order 2, 5, 10% in radius. Now, if you know anything about galaxy surveys, within that volume, there are literally millions of galaxies that could be the source of that black hole. So we don't really know which galaxy is or which redshift that is. It can be anywhere. Okay, so you can never do this object by object. What you can do, though, is to do this statistically, which is what we found a way of doing. So basically, you overlay those two maps and you look for a correlation, right? Because if you are missing the distance, so if you're assuming that your distances are larger than what they are for the given redshifts, then the two maps mismatch. And these two are weakly correlated. If you miss the other way, if you say the distances are too small, you again have a mismatch because your correlations are weak. But if you get it right, then the correlations are stronger because you find things that are statistically close to each other. But how statistically and how you do this, that was a question that basically nobody was able to do this in a sensible way, and that's how we found it. And this is the answer here. This is how you do it. And it's extremely simple. Basically, we have these, sorry, let me go here. So we have these maps of the black holes that we have in shells of distance here, okay? And in the same area, we have a map of galaxies that are in bins of redshift. So our slices, our radial slices, are different. One is for distance and the other is for radius. And then you correlate everything. Angular correlations, everything. And this is what you get here, okay? This is the entire correlation of 100 shells in redshift with 50 shells in distance, okay? And that's what it looks like. So here is the galaxy-galaxy autocorrelation in redshift. This is the black hole autocorrelation in distance. And these are the galaxy black hole cross correlation with the galaxies in redshift bins and the black holes in distance bins. Okay? And what you see here emerging in front of your eyes is exactly the Hubble relation, the L of Z. Nothing else. Okay? And of course, there's information in here, there might be information in there, but this is new information. The only information that we can get about distances from the autocorrelation of galaxies is basically what's in the baryon acoustic oscillations, which is a very close up in this part of the plot here, and you look at these oscillations, it's a whole different game. We are not talking about this at all. We're talking about this. This is a completely model-independent way of getting at the distance. So this is a model-independent way of doing cosmography. Okay? So that's basically the idea, is that we have these cross correlations. Again, you divide your sky into redshift bins that are appropriate for your galaxies. And in your other hand, completely independently, you get your black holes and you put them in slices, in radial slices and radial shells of distance. They are not related, okay? It's not like we use any model to do this. You just do this whatever way your experiment tells you to do. And then you cross-correlate everything, and this is what you get. If you now test your cosmological model, if you have the right one, then it's this black line here. But if you get it wrong, then let's say this ridge here, this highest correlation will fall here or there. So it's a direct test of the L of Z, the simplest thing you could imagine, okay? Why does it work? Well, think about the correlation function of matter in the universe. We know that has a very peaked curve like this. So this is a two-point correlation function in real space. And this tells you that things are highly correlated if they are nearby. And If they are farther away, the correlations fall very quickly. So this curve here is relying on the fact that if you are close to the actual, so suppose that here at R is equal to a galaxy, and you're placing a black hole in here, nearby, let's say 1 megaparsec from the galaxy, then you will be over here. You will have a high correlation with that. But if you are over there, it's a low correlation. So all that matters for this curve here, all that matters is that the correlations are higher when things are close by. So this is a statistical way of measuring things. If for your entire sample, you have a higher correlation, which is over here, that means that all objects are closer. If they are weak, then they are far away. That's it. Oh, yeah. This curve here, the fact that it's very broad in here is directly because the dark sirens, the black holes, they have a large error. Here, this is an exercise using Einstein telescope. So the huge, you can imagine that this is distance here, right? So the huge error that you have there is because of the error in the instrument, in the Einstein telescope, to give you a very accurate distance, right? Because we don't know it to, 2, 5, 10% sometimes error.
How many merger events are you considering there in the black?
In this case, this is I think 30,000 merger events, which is something you would get in maybe 2 years, 3 years. Yeah. Yes. Right. So this is, again, different L's will carry that information. So in our case, that might be a bit more technical. I have a slide for it later if you want to know, but very high L's, they are suppressed because of this, let's say you smear out the angular position. Yeah, it depends. So for LIGO, for LVK, LIGO overcarga, the highest L that matters is about 100, 150. For Einstein telescope, you can go up to 300, 400, because you have some high signature noise events, some not so much, right? I have a slide about this exactly later, all right? So is this clear now? So it doesn't really matter if your 2-point correlation function is like this, or like that. It doesn't matter. All that matters is that it's highly peaked. That is what gives you this ridge along here, right? Of course, we are relying here on the fact that there is no systematic shift in the distances, right? But then you go back to the relationship between the waveforms and the distances. This is, again, black hole mergers are the hydrogen atom of gravity. So nobody believes that there's a systematic problem with the distances. There's an accuracy problem, but not a precision problem. Okay?
And Raul, do you get any information then from the mass spectrum of this hydrogen atom?
Zero. It doesn't matter.
So
the masses of the objects only come into play for the signal to noise for the angular position and the radial position. That's when they matter. But it doesn't matter what they are. It's like we don't care about galaxies. We don't care which galaxy we're mapping.
But then you get that information out from breaking up the...
yes, that's one of the things we are working on, right?
Okay.
When we break the degeneracy, we can then retrieve the masses by inverting that without any model assumption, right? Anyway, so I'm just repeating things here. So the method depends just on the fact that your correlation function is highly peaked. So it doesn't matter which model you are using for the correlation function or the power spectrum. In fact, our method is completely oblivious to this. You can play around with the correlation function as you wish. That doesn't affect the model at all, the method at all, okay? But it does depend on the number of objects and the signal to noise. So better detectors will give you a better signal and so on, right? Also, it doesn't matter that the exact galaxy that is the host for those black hole mergers is in our galaxy catalog. That doesn't matter. We in fact take it out completely and the effect doesn't change. So there is an assumption here, of course, that it is that the black hole mergers are happening inside galaxies somehow. So that's it. I mean, so if you don't believe that, then, that's fine. So what we do is that we do thousands of simulations. We do simulations of the whole sky using this code here called GLASS. So this is one example of one simulation. We did basically order of 50,000 of those simulations. We use realistic redshift-dependent samples for the galaxies. So we actually use a very low number of galaxies, about 30 million for the full sky up to redshift 2, which is ridiculous. I mean, Euclid alone is going to have like, I don't know, 10 times that in a smaller area. So this is very conservative here. And then we also simulate the events using the latest techniques which are directly derived from the instruments themselves. So you learn from LIGO and then you forecast for Einstein telescope, and then you simulate the black hole merger events, which are here. And what you see here are blobs. And why blobs? Because of the error in the angle and in the radial positions of those objects. So they become basically clouds, and we use those clouds to, mitigate the errors in the positions. Of course, then there's a whole thing that we use, Hill peaks, Namaste, which is maybe familiar to people that does angular correlation function, angular power spectrum. Okay, here are Jorge. Maybe this answers your question. So this is the error in the angular position, okay, and this is the error in the distance. So relative error here in the distance and absolute error in the angular position. You see that for LVK, LIGO, Virgo, Cagra, you have typically objects which have between 10 to 100 square degrees of uncertainty in the position in the sky, and 10% to order 1 errors in the distance. So very uncertain measurements. For when you combine LIGO, Virgo, Cagra with Einstein telescope, what you have is this. So many tens of thousands of events. Some of them are not well placed, not well localized, and that's just because of geometry. Sometimes they are in a region where you don't get the best of the two detectors. You just see them, for instance, if detectors are aligned, then you don't see this event too well. But if they are perfectly aligned, then you see objects which are much better resolved here. So there's a variety of sources. Some are well localized, some are not, and we take them all. It doesn't matter because we are doing statistical measurement. In fact, it turns out that combining LVK with Einstein telescope, you are already almost as good as if you were combining Einstein telescope with Cosmic Explorer. So actually, it's good news, means that earlier than we thought, we could have very good results for these things. So this is the simulation that we're doing. Here is one particular slice at redshift 0.25. So we cut out the galaxy. So basically, because of the galaxies, the observations of galaxies, we don't see behind our Milky Way. So we cut out the Milky Way here. So that's about 1/3 of the sky. And then this is the sensitivity for the gravitational waves. This is due to the fact that the detectors are placed in some geographic place on Earth, and Earth rotates, but there are some regions which are in which this is more sensitive than others. Then you have the galaxy map, and then you mix the two in the simulations, right? And here finally are the results. Okay, so if you have just LIGO, so LVK run 05, which is the run that's going to start in next year, basically, okay? This is the constraint we get with our putative galaxy sample of 30 million stars, 30 million galaxies, okay? So what you see here is that we can get, if we are only fitting for H0 using that distance redshift relation, we can get a 4% error in H0, just with that. So within 3 years, we can get that kind of a measurement. That's our forecast. If you then make a more general fit for both H0 and omega matter, which is what you actually should do. Nobody in the community of gravitational waves in H0 does that, but this is what you actually should do because, the distance redshift relation, it's only for z equals to 0 that it doesn't depend on omega matter. But if you go to higher redshift, then it depends and they are degenerate. Then our constraint then changes a little bit to about 7% in H0, okay? That should be compared with everything that we have included in the kilonova, which is right now giving you about 6%. That's the precision that we have right now with every single gravitational wave from neutral stars and dark sirens and everything that we have is over here. So this is very competitive. It's a new way. It's independent from the others, and it's already competitive. It's going to be in 2 or 3 years. 3 years, maybe 4. Now, what about the future? What if we have Einstein telescope also in the game? Well, then we get the accuracy down to 1%. That's what we expect to get. And with Einstein telescope plus 2 cosmic explorers, so that's maybe like 20 years in the future, that's down to 0.7% in H0. Okay? So again, this is LVK plus ET. So if Einstein telescope gets funded in Europe, it will start to be built around 2030, start taking data 2032 or so. And then in 10 years, we might be seeing something like this. That's our forecast there. You can also do full forecast for cosmology, which is pretty much like baryon acoustic oscillations, because it's really the same game. And what we get is something like this. It turns out that it's very similar to what you get from usual sirens like supernovas, because it's really, you're testing basically the same thing. But in the case of the gravitational wave observations, it has no calibration. It doesn't depend on any of those calibrations, so it doesn't have the systematics. But here it is what you get. Of course, when you include enlarge a set of parameters, your constraints get worse. But that tells you also that there's lots of room for combining this data set with other data sets. That's what this is telling you. Okay, now I think I'm going a little bit over time, right? Yes. I need like 3 minutes more. Let me just say that what is different about this method here is precisely the fact that it doesn't need calibration. That is, in principle, free of systematics. But there's never such thing as free of systematics. So we did some stress tests. So first of all, what if you change the shape of that correlation function? What if the correlation function, you assume that comes from one cosmology, but then your model comes from something else? It doesn't matter. We did a test with a fiducial model was completely different than the Planck cosmology. And then we fitted for that using a different clustering. You recover the right thing with basically no bias at all. So it doesn't depend. You see, the argument doesn't depend on the shape of the correlation function, only on the fact that it's highly peaked. That's it. Other thing is lensing. Turns out that lensing was something that people were worried about. And we figured out that there's a very little concern. It's only if you completely ignore lensing that you have about a 0.2 sigma bias. That's in the Einstein telescope plus two cosmic explorers. That's in this futuristic. And that's by completely ignoring lensing, which is unrealistic. So lensing modeling will just solve that. And finally, the most important thing is lensing. Well, yeah, good. So lensing magnification works for gravitational waves as well, right? So if you magnify slightly the signal from a gravitational wave source, you assume that that distance is closer to you than what it is, right? But it's a very small effect. It's here, okay? So it changes your correlation function to large. So this is magnification here. This is demagnification. So it shifts the things just a little bit, but it's basically very negligible. The peak here, it almost doesn't change, which is what our method depends on. And the last thing I want to say is that, well, what about nonlinear modeling, which is the bane of our existence if you're working on large-scale structure? Theory is always, now it's, the whole community is totally concerned on getting more and better ways of predicting the theoretical underlying matter power spectrum if you have nonlinearities. Well, in this case, it's totally irrelevant. If we use a model which is a linear model, which is the simplest thing you can imagine, and if we put a very strong nonlinear fit for the power spectrum here, does it change anything? No, it doesn't change anything. The method continues to be there, right? Yeah. No. We are. Here is the nonlinear scales change the shape of this here, of this curve here in the very center, but it doesn't change the fact that it's peaked. It doesn't bias that peak. The peak is always like this, right? We are smoothing over this region here, but we're relying on the fact that the correlation function is growing. And it doesn't matter how it grows. In nonlinearities, they tell you, they give you that. They change that slope. Yes. basically. So let me just conclude, because otherwise I'm running too much out of time. So as far as every single test that we conducted so far tells us that this is a robust method, that we don't need calibration, that it's independent of pretty much anything we tested. So we can now use the vast majority of gravitational wave observations without the need of kilonovas. And we can get it within 3 or 4 years about a 4% constraint on H0 that's completely independent of the other constraints, and 1% in 10 years. And we have many things to do, but one of the things that we're doing now is that we are working with real data from LVK Run 03, together with Isamatos and the people in Portsmouth. Let me just tell you a final anecdote. The anecdote of this problem was like this. We cooked up this idea about like 18 months ago. And we thought, well, surely this cannot be measured anytime soon. Then we made a simulation with the Einstein telescope and Cosmic Explorer. And then we get this 1% error. And then we spend the next year testing this because we thought it was too good. Then we do everything we can. We show too many people, it's there. And then we said, okay, let's now just do Einstein telescope with LVK. Then 1%, well, surprising. So let's do now LVK by itself. And then we get a 4% constraint. And then we say, okay, now we should test it with real data right now because there's no reason to wait. And this is what we're doing now. So that's the end. Thank you.
So very impressive, Raul. I'm impressed, yes. Any questions or comments in the room? What about LISA? I mean, I guess it's a completely different frequency regime, more massive objects, less statistics, I guess.
Yeah, LISA has a much lower frequency band. Yeah. So it's going to be observing supermassive black holes and very much higher redshift and many less events. In many cases, it won't be able to pinpoint where they come from. It has a different science, right? It can be sensitive to, fundamental physics things. As a map of the universe below redshift of 20 or so, it's not a very efficient map because it gives you amazing physics, but not cosmological physics.
All right.
Einstein telescope for that is like
deeper.
Super.
What is the time scale for Einstein telescope if it gets approved? What is
so
10 years?
if it gets approved, it can start construction around 2030, and then it takes maybe even earlier. So best estimates is that it could be start working in 2032, something like this. Maybe a bit later. Yeah, it depends very much on funding, right? The 10 years is from now. So I'm assuming that by 2035, there will be something like 2 or 3 years of Einstein telescope data already. So maybe that's a bit optimistic. I don't know. Depends on Europe having funding for science, not defense. Huh? Right.
Thank you, Raul. So quite impressive. So I wonder what is the comparison with the forecast for the bright sirens. So I saw in the slides, I think for 04, so the forecast is 7%, but what about 05?
Right. I don't have it off the top of my head. Let me see if I recall. They are comparable, but it depends very much. You see, these estimates, they depend on some completely unknown rate of kilonovas. So far, we have had one, and possibly another one that was missed, but it's uncertain, right? But we have just one. So the estimates, that estimate depends on a huge, very broad assumption about how many of these objects we can get. So it's not like Einstein telescope will give you many more of these events. I mean, LVK is already sensitive, and it has detected that one. So if we see 100 of those, then that will be for sure the best way. But it's uncertain if we ever will. And if they happen at higher redshifts, that will be detectable by Einstein telescope because they are lower frequency because of redshift, right? But they might not be ever visible because it might be so faint and redshifted that we won't be able to find it for practical purposes, unless something magical happens like a gamma ray burst at the same time that helps us pinpoint. It depends it depends on assumptions across all these multi-messenger spectrum and the populations, which is just, people don't know too much. So the estimates they vary a lot from, 0.5% to something of the order of what you're seeing here now. Right.
So actually I have a few more questions, but I ask one. So basically you're proposing a method to determine each node that is almost free of systematics, although, the ones attached to the measurements of the distance themselves. So you publish this paper, you have what the reaction of the community to because I find this
so far always good, but
Okay. So
this is included now in this science case is included in the Einstein telescope white book, blue book, whatever they call this, the white paper. So it's part of the science case for the Einstein telescope now. We literally have this paper out for 2 months. So, I'm looking very hard to find where are any possible holes in this, what possible systematics there could be, because there will be for sure, right? There's no such thing as systematic free, never. It's just that we have to look harder. And I have given this presentation just about 2 or 3 times to expert audiences. So I'm eagerly waiting for people to point me to a direction where I could stress test this more and find ways in which this can be generalized. So I think the most important thing right now is the thing that we are working on, and which is which kind of galaxy catalogs can you use? Because of course, the selection function of the galaxy catalogs will have an impact. And knowing that, will have an impact. So whether we prefer more galaxies with a less known distribution, or if you prefer a smaller set of galaxies for which you understand very well how they are mapped in the sky, it's exactly the type of thing we're working on. But, if somebody else gives other suggestions, we are totally open. We're just beginning in this.
I was wondering which kind of catalog are you using now for trying to measure it with real data?
So we are using something called the Glade Plus.
Yeah.
So this is the stuff that people in LIGO have been developing, which is a very low redshift amalgamation of many different surveys in the B and V bands mostly. So it has a complicated selection function, but it's nearly full sky in the sense that it has everything except the Milky Way. That's what Isa and Tessa and Charles are working on. Charles was one of the builders of this catalog. But it's a big question whether this is enough.
Yes, so like I assume that probably this will be more limited from the black hole side, but then it also matters like the area you have, or probably the redshift accuracy. I don't know. It's also a factor.
Sorry, I don't get it.
I mean, like I assume that the problem is limited from the gravitational wave side, right?
From the gravitational wave side, it's very simple. It's really the distribution is pretty much what I showed in here. This is the sensitivity here. They see the full sky, right? They see everything, right? With a different sensitivity. So you want, of course, you would like to have more galaxies over here and there, but we get that already anyway. This is so the galaxy map will it better cover the largest area that you have, because the gravitational waves, they don't really matter. They don't really care too much. You see gravitational waves from literally every direction in the sky.
Yes, so you might prefer like a full sky catalog with lower sources rather than, for example, like something like DESI or whatever.
Anything goes, in fact. I mean, it's the big question, I think, in order to control systematics better, is to have galaxy catalogs for which we understand very well the selection. That, I think, is the key. So I would not include catalogs which are, pencil beams here, small one there, for which, they kind of, you don't know how they were selected. This is, I think, would be the main problem there. So exactly which ones, I don't know. So I think that a combination of both photometric and spectroscopic could work. But that's exactly what we're looking into now, making different tests with different, let's say, different shapes of galaxy surveys.
Okay, thank you.
Yeah, some technical one here.
what is the width of the shells that in redshift that you're considering, and whether you include peculiar velocities, whether redshift space distortions or radial peculiar velocities of galaxies make a difference here?
Yeah, good question. We did not include redshift space distortions here. The redshift bins are 0.02, which is large enough that, you know, redshift space distortions are smeared out inside, but not so much. But they are dominant. But we could have used twice that, because the bins, you see here we have 50 bins between 0 and 15 basically gigaparsecs. So you make the calculation. So these are 30 megaparsecs, 300 megaparsecs, something like this. It's my guess is that with these bins, the redshift space distortions will be smeared on the side, but we haven't included them yet. My impression is that they are going to be, they're just going to introduce a little bit more smearing, but compared to the smearing that you already have from the gravitational waves, it's totally subdominant. But that's one thing which is in my conclusions that include redshift space distortions right there. It's here. We haven't.
Oh,
yeah.
Yes, sure.
How do you choose how you've been in redshift and also in the luminosity? And does the cross correlation depend on the binning?
Yeah, I mean the shape here depends, of course, on the binning. But that's just if you know what the binning is, you can do any binning that you want, right? It doesn't matter too much. Of course, you're gonna find a fit for DL of Z, right? So if you use different binning, that figure here, which is, let me just use this one here, right? So this one is just square because I chose it to be. But you know, this axis has in principle nothing to do with this one here. So you could see this as something like this, something like that, or even with uneven bins, it doesn't matter too much because you're fitting for the L of Z after all, right? So the binning is important in the sense that you don't want to smear out the information and lose this peak here. That's what you don't want to lose. But you see the peak is broad enough that you can use even larger bins and it will be basically the same. The choice of binning here was a bit arbitrary, but it will ultimately come from your survey. So I would say that, for instance, if you're using a photometric galaxy sample, then your bins in redshift would have to be wider than 0.02, right? They'll have to be, I don't know, 0.05, something like this. But if you're using a spectroscopic sample, they could be smaller, right? So this figure here, we'll actually have many of those. We'll have something like this for a photometric sample, something like that for a spectroscopic sample. The binning is like, it's easy. It's much easier than in other situations, actually.
Okay, I think we have to wrap up. So let's thank Raul again for his talk. And I also want to end the session by saying that I saw a record in the followers in YouTube following your talk, like 16, when typically it's 1 or 2. So
okay,
that also speaks
cool.
about the interest.
I'm happy. Well, we didn't see if there were any questions.
No, I was checking, but there were
yeah,
not.
right, okay.
Okay, thank you very much.
All right, thank you. Okay, I'll turn off here the Zoom session then. Cool.
Guys, PhD students, can you all pass by in order to write your names down? Thanks.